Hello, everyone. Thank you very much for joining me today in a talk all about a wonderful cocktail of mixing beer, IoT, and .NET. The inspiration for this talk came from a conversation I had with a good friend. He has a rather impressive homebrewing setup with a brew Pi, Raspberry Pi running Python-based code. And it was admittedly over a couple of beers. Then I got the inspiration and the challenge to say, well, what could I do with .NET, with purely .NET? So anyone that doesn't know me, my name's Shaun Lawrence. I am a .NET-based developer. Shouldn't come as a surprise. I've been working with .NET roughly for almost 20 years, and I've been actively researching good beer for even longer. I will say that this is very much a hobby project rather than a professional project, although my day-to-day job does involve working with microcontrollers, so there is some level of understanding there. And I suspect you have heard the two letters AI mentioned a lot throughout the conference so far. This is the only time I'm going to mention it, and that's purely because I was somehow able to prompt Microsoft Designer to generate that logo. So I did rush off to the printers, and I've got some stickers up here if anyone wants after the talk. I'd like to begin by quoting a wise old proverb, which is give a person a beer and they'll drink for a day. Teach them to brew and you'll give them a hangover for life. They do say you always remember your first time. Sadly, actually, my camera roll does not. So I've had to Google for some images here. But essentially, my first attempt back in 2008 involved buying a lager kit from a local DIY shop. Mixed the ingredients up in a bucket a bit like this. Then wrapped it up in a towel. I thought that would work well. And I stuck it inside of an airing cupboard. Which actually, I mean, lager actually works surprisingly well. It needs a fairly low temperature, so it fermented over the course of 2 weeks. And luckily it didn't taste too bad because there was 40 pints worth of it. So rather an ambitious first attempt. For now, I'd like to take you through what the brewing process entails, and then we can start to look at how that could be automated. So the first thing with any kind of recipe that you would follow, whether you're making a meal, whether you're brewing beer, is to make sure you've got a clean environment, make sure all of the utensils are clean. Following on from that, then we go through the process which is called making wort. Now, if anyone's not familiar with wort, it's essentially a liquid that you make from grain, and then you end up turning that into beer through the use of yeast. It's only a single bullet point there, but it is a rather involved process. It involves mixing in water, boiling, changing the temperature, adding hops at different times, depending on the bitterness that you want in terms of the acidity that comes from the hops. And then you end up adding malt, chilling it, and then aerating it, which then prepares it for the fermentation phase. Fermentation is a case of sticking some yeast in it, covering it, keeping it warm, and leaving it for a process of 2 weeks, roughly 2 weeks, depending on what it is that you're brewing. Then after that comes the carbonation stage, which depends on what you're brewing in. So if you saw on the previous slide I had a bucket, you wouldn't typically carbonate it in there because you want to be able to drink it straight out from there. So you'd either transfer it into something like a bottle or a keg that has a pump in it, a tap. And actually, so both the fermentation and the carbonation phase actually currently involve a good level of temperature control, which might give you a hint as to where we're going today. And then finally, one concept which has become quite common in home brewing is this concept of cold crashing, which is once you've reached the carbonation stage, you then drop the brew down to refrigeration temperatures in order to then kind of make sure that you kill off the yeast and anything else that you don't want in there. That will all then drop to the bottom. If there is anyone that fancies learning how to brew, I would thoroughly recommend this book. It certainly got me going in the early stages, but even now it's huge. It's, I think, about 600 pages. My daughter even commented how on earth I get through it because I'm not the fastest of readers. But it's packed with recipes and all of the lots of details in terms of each of these individual processes that you might want to look into. And to lead on from that book, there is an excellent 5 bullet points that he suggests, and I'm going to quote them today because this is going to lead into what I believe we could automate. So the first one is sanitation, and ultimately that means keeping things clean. Don't worry, I'm not going to break out into another clean architecture talk here. But basically, because you are you're going to be dealing with yeast and you're brewing something for a period of time at relatively warm temperatures, you want to make sure that the yeast is the only microorganism growing inside. Next we have fermentation. I mentioned yeast. This is a case of where we put the yeast inside of the mixture and then we leave it for a period of time. And as I mentioned before, that good temperature control is key for this. The third highest priority on John's list is proper yeast management, which sounds a bit of a strange term to be saying on stage. But essentially, it typically involves buying good quality yeast or sourcing good quality yeast and making sure you use the right amount. You don't want to make your brew too potent. And then we've got the boil. So this is with any recipe again, if you're going to cook a meal, you want to make sure that the ingredients are cooked properly. You don't want to have to undercook it or overcook it because then you are going to spoil the taste of your beer. And that's the main reason we drink it, isn't it? Is for the taste. And then finally, we have the recipe. Now in John's list, this is the mixture of ingredients to create a good blend and a good tasting beer. And I don't disagree with him, but in terms of the project that I've been looking at, I'm considering this more a set of steps that can be followed. Because if you imagine we're going to use an IoT device, it's going to have a job, but it's not going to do that one job at the same setting throughout the course of the brewing operation. So if we now take this list and then we consider how we could automate each of these steps, I've handily formatted this for you already, but sanitation I don't think it's necessarily the easiest thing to automate. I mean, we could put it in a giant autoclave or something like that, which pumps it up to a high temperature to clean any bacterial or germs. But rather than crossing off, because it was at the top of the priority list, I'd like to consider this I have considered this as a requirement of the operation. So the way that I've seen it is, I can interpret this as to say you want as fewer components as possible that are actually going to be exposed to the brewing process, because then you make it much easier to clean moving forward. And ultimately, your components will be much easier to maintain because you're not exposing them to things they don't need to be exposed to. Then we have the fermentation phase, and that involves, I think I've said this a number of times, good temperature control. So that will be something that we can automate, and we will see how to. Again, proper yeast management, I've said it. It's buying good quality yeast and the right amount. You could automate half of this by setting up a direct debit to your favourite supplier. The boil, I'm crossing it off. Now, it does involve temperature control. However, if you consider, certainly my cooking skills, I make a big mess when I boil, so that's then going to conflict with point one. But then there's also the concept that you're not always going to be guaranteed that the same ingredients will always cook at the same rate. If you compare it to a packet of pasta you might buy from the supermarket, the boiling time on the side does not always match reality. So some form of visual manual checking there is typically quite valuable. And then finally, I mentioned the recipe being a set of steps. We can then use this to tell the IoT device what it needs to be doing, or allow it to ask. So we've covered that sanitation was crossed off the list, but it's not something we'll look to implement. That then leads us on to the fermentation phase. Now, I'm personally a fan of IPAs. I don't know about what other people prefer. They typically have a kind of higher range. They like a bit warmer. So you have an ale yeast and you have a lager yeast. Ale yeasts, they will typically ferment at the top of the brew, and they like it between 15 and 22 degrees Celsius, or 60 and 72 degrees for our overseas friends, Fahrenheit. And then the lager yeast will brew at the bottom, and that's typically between 7 and 13 degrees C. And I mentioned, so my first brew was a lager, and that benefited much from the climate. There wasn't really much to do. It was spring. I kept it in the house. I put it near the airing cupboard, but we didn't necessarily have the heating on that much. But then I guess when you start to consider climate being a factor, if you look outside, that's probably much more beneficial for a cold crash rather than actually fermenting it, certainly an IPA anyway. And you wouldn't want to necessarily be heating your house just to keep your beer happy. Certainly it's not easy to justify. But temperature control is easy, right? You could set up a heated blanket, a smart plug, and use a smart thermostat, and you can set it up on your phone to turn the blanket on when you want to and turn it off when you've reached that temperature. But this will actually lead into a fair amount of inefficiency, which is something we're going to look at and how you can avoid that. The recommended way, the way that I've chosen to do this, it's certainly been influenced by others, is to create something that's called a fermentation chamber. So essentially what you do is you insulate a box around the brew, and then you can then regulate the temperature within that. And quite often people will hack a fridge in order to achieve this, because it's already got good insulation. It can keep beer cold in summer. It just doesn't have the heater element, which we can look to implement. But I hope you will forgive me. I didn't fancy lugging a fridge around. So what I've actually done is I've hacked a cooler box, and I've brought that in here. So we've actually got the full IoT set up in here. I had to message my wife because we've been doing exercise videos at home, but I can safely say I'm no healthier and fitter because that was quite a struggle to bring it to the hotel. And now I do appreciate this is quite small. Obviously, people might not be able to see everything. When we get to the demo time, I will stream anything onto the screen, but I do hope there will be a bit of time so people can come up and have a look and poke it if you like to. So I mentioned the fermentation chamber. So essentially what you do is you put a box around the thing that you want to keep warm, and rather than regulating the temperature inside, you regulate the temperature in the chamber, and that will then eventually transfer into the liquid. So in terms of knowing how you're going to regulate that, I mentioned that we would regulate the temperature in the chamber, but if you actually want to monitor the temperature, you want to monitor the liquid temperature. Because if you consider monitoring here and you're heating in here, you're going to get a lot of noise, and actually you're not going to be able to necessarily be able to do things efficiently. But once you are able to monitor the temperature of the liquid, you can then consider my terrible drawing of a heater element there. You can stick a heater element. I wouldn't put it directly underneath because, again, if you want to cook something, you don't want to cook the bottom and leave the top at the right temperature. So quite often you'll put a grill between the two, or you might even put the heater elements at the side to allow you don't have a direct contact to the heater element. Because I've got a little 12-volt heater in here, but that can reach up to 70 or 80 degrees. So I certainly wouldn't recommend putting the keg straight on top. We can then put a fan inside, so we could circulate the air to make it easier to regulate. And this cooler box does come with a fan attached. It's typically designed for sucking air out rather than creating good flow, so this doesn't actually turn the fan on when you heat. We just rely on that because it's a small space anyway. I actually became quite confused when I took this out of the garage because it had a warming function on it. So I started to question whether I even needed to do anything for this talk. But it turns out it just pumps in warm ambient temperature rather than actually, there's no heating element in there. So the other thing that I've decided upon doing is actually measuring the ambient temperature outside of the device. Because when we start to look at efficiently heating and cooling, if you're saying that say it's 10 degrees outside and you want to keep the beer at 21, as you're going up, you'll eventually hit 21 and then you'll decide to turn off, but you will overshoot. You won't stop at 21 degrees. You don't want to then turn the cooler on if you know that the ambient temperature is lower, because it will just naturally fall down. So therefore, you can actually use the environment to aid you there rather than being inefficient, because if you turn the compressor on, you're going to drop and then you're going to have to fight it back up again. So it's not very green if you're going to keep turning on the electrical components just for that purpose. And then there's other things that people have considered. You can put a pump in there so you could actually make the beer flow around, but you then ultimately end up exposing more elements, more components to the brewing process, which we don't want to be doing. There are pumps where you don't actually end up exposing the pump to the liquid. You just expose the tubing but ultimately you'd have to clean the tubing or replace the tubing, and again, that's not particularly environmentally friendly. And then what's a common option in the field that I work in, the pharmaceutical industry, they actually, to keep their solutions happy, they rock them back and forth, a bit like trying to put a baby to sleep, with a gentle motion. But then if you imagine we've got 40 pints that we're trying to brew, you need some fairly heavy machinery or mechanics to actually support that. And those are more moving parts, which I would certainly like to not maintain. And then the only other thing that I haven't drawn on this diagram is the compressor, the cooling element that comes with the fridge. Hopefully that's just implied by the box. So now that we've got the concept of a fermentation chamber, we then need to actually look about how we can control the elements within that fermentation chamber. And I decided to use what's called the Meadow F7 featherboard, which is a board that came about from the Xamarin team. Some people broke away and decided they wanted to do IoT, so they then developed a board that can run .NET, and it ultimately runs on top of Mono, so it's a very similar kind of environment that you would expect to the Xamarin world, obviously with limitations on what you've got that you can achieve. And so to quote them, it's a full stack IoT development environment. You can build .NET applications that will run on it. It runs, it's not like a Raspberry Pi. There's no desktop. There's not a lot of operating system there. It is a micro real-time operating system that typically means if your application crashes, nothing's happening. Whereas it doesn't crash to the desktop like you would expect with a Raspberry Pi or a PC. It comes with some fancy features like BLE, hardware encryption, Wi-Fi off the board. I haven't used the BLE side of things, but the Wi-Fi works remarkably well. We've got a garage that's not attached to the house, so there's a gap. And we do, surprisingly, get reliable coverage there, which is great. I can certainly know when things are not behaving. And I'd like to just highlight on the middle to left bottom there, the 32 megabytes of RAM that it comes with. And compares back to a device, the Pentium 200MX from 1997. Actually, I mean, Google was not happy with me. When I tried to search for a 32 megabyte RAM machine, it kept correcting it to 32 gig, because why would anyone want to buy 32 meg of RAM? But this is not to put the board down. It's purely to highlight the limited resources that you will have in an IoT environment. And actually, during the development process for this, I ran into thread exhaustion a good number of times, because you're limited to 32 threads, and it can sometimes be quite easy to be a little foolish and just spin them up without realizing what you're doing. But don't worry, there are parts of this talk that will show you how to avoid that. This itself, the Meadow this is the V2. There is also a V1 which kick-started back in 2018. I know that I did kick-start it, and then I'll hold my hand up and admit that I left it in my airing cupboard collecting dust up until post-pandemic, when I then got the kick to actually try and do something with it. Keep getting static. We've got so I mentioned that we've got the real-time operating system. So that real-time operating system is called NUTX. It's an open source real-time operating system, so out there in the world that you could check out. On top of that, you then have the .NET runtime, which is Mono. You've got the OS services, so you could hook into sleep APIs. So if you don't want your device to be constantly polling and checking whether it needs to be doing work, you could put it to sleep. So we put a solar panel on it and we put it out in the field. We could keep it going without necessarily, or try to optimize how often you use it so you're not going to keep consuming too much power. And then it comes with things like crash reporting and health monitoring. The Meadow team do supply a cloud-based service, so you can actually hook this up, and then you can hook into over-the-air updates and things like that. As part of this project, just to keep Maddie happy as well, there's an Aspire logo on here. In terms of the health monitoring and the crash reporting, I'm in the process of trying to work out how we could send the logs from that up to the Aspire telemetry endpoint, so you can then have all of your logs in a single place. On then Above that layer, we then have the Meadow core. That's essentially you then get to be able to open a port, connect to an analog output port, analog input port, digital output ports, or digital input. I think there's 16 digital ports and 6 analog ports on this, so you can interact directly with them through the Meadow core libraries, and these are all NuGet packages that you can consume. There's quite a variety of them. And then on top of that, you've got the Meadow Foundation, which is typically more specific peripheral support. So there is mention there of the BME 680, which is quite a go-to sensor to be able to hook in and tell you what the temperature and the humidity is in the room. It comes with a fair number of support for a fair number of devices. Not all of the devices that I needed for this, so I can show you how you can actually achieve support without the Meadow SIEM already providing that for you. But just to take a little bit of a step back to give you some context before I can then actually start to show you some code. I mentioned that this is it's running in a real-time system, a real-time operating system. An application running on one of those devices is quite different to a business application. So a business application will sit there waiting for input from a user, whereas in a kind of a real-time system, you implement what's called a polling loop, where you'll sit idle for a period of time, just so you're not constantly working. Then when you wake up, you'll then do some work, and then you'll go back to sleep. In this slide, I've tried to split it out to a read and a write, so in theory, you could try and maybe create some form of immutable state and then react upon that state, rather than doing both in one. And it hopefully aims to kind of reduce the complexity of the code that you write. And then this is also quite similar to another topic that's quite dear to my heart, which is game engine development, where the read would be like you'd update the state, and then the write would then be rendering, and that's on screen. So it follows that kind of pattern. So now that I've talked about the chamber, we've talked a little about the technology, we can then start to look at each of the individual components. We've got an ambient temperature sensor here, and then we can then see the code to implement that. This type of sensor actually will output a voltage dependent on the temperature. So if I come over here, what I can do is I can show you the code that runs this ambient temperature sensor, and you should hopefully see that it's not many lines at all. So I will add, this is Visual Studio Code because I'm working on a Mac, just to make my life more difficult. But they have an extension for Visual Studio 2022. There's an extension for Visual Studio Code, and then there's also a CLI, which this extension hooks into. Is that fine? I can zoom in a little bit. That'll make it really difficult to see then. But essentially what we see is we have this concept of a temperature sensor. We can then hook into the port, so we tell it on the board itself, we're hooking into analog 1. And then Meadow does also ship, like I said, it ships with some level of support for existing sensors. So if I was to go here, you'll see that there's a number of different sensors that they do support. And that just ultimately then comes with a set of configuration to determine the voltage that's coming out of that and what that means. If you buy one of these types of sensors that it doesn't support, you can then just provide the calibration. You just have to sit there with a voltmeter and try to work out exactly what it's outputting. If we skip past the next line, the line I've got here, 22, we then, once we've created the sensor, you can then just tell it to start updating. And this is how you run into thread exhaustion sometimes if you're doing it too many times. Ultimately, this ends up creating a thread in the background, and it will then keep this temperature property updated for you, so you don't have to keep reading from the sensor. It will keep it up in memory for you. Now, to avoid that extra thread being created, you've got this line above, which basically there's a central service. You can register your sensor with it, and then it's got its own kind of loop. So you can't read any quicker than, I think, at 5 seconds. for each sensor, but in a project like this, that's perfectly acceptable. Not all sensors support that sensor service. They don't support a shared polling loop, but it doesn't mean you're going to get an exception. It just means it'll revert back to the previous implementation. So you don't have to worry about knowing which one supports and which one doesn't. So that's a fairly typical standard sensor, and it does come in the dev kit that you can get with a Meadow board. Probably fairly easy to pick up off RS Online or somewhere like that. But in order to monitor the liquid temperature, if I jump back aside, I don't fancy dipping this in the liquid because obviously the terminals are exposed. You're not going to get a good reading. You're going to short. So I decided upon this. So as I mentioned, some of the work I do is in the pharmaceutical industry, and they use these where I currently work to check whether the solutions are at a suitable temperature. They're not particularly expensive, so I thought I'd pick one up and just plug it in. It would work, but that's not the case. But what I will say is, all of the Meadow work is done in the open. They have a Slack, and I asked questions about this, and they directed me to solutions, so they're particularly helpful in this. Essentially, this is what's called an RTD, so it's a resistance temperature detector. So with the old sensor, it changes its voltage based on the temperature. This one changes its resistance based on the temperature. It's called a PT100, which means at 0 degrees Celsius, it's 100 ohms. There is also a PT1000, it's 1,000 ohms at 0 degrees. But like I say, you can't just plug that into the board and it will work. You have to buy one of these, which is an amplifier, in order to be able to get a suitable signal out to detect what it is that you want. And I was unable to find any examples of how to do this with a Meadow, but there are blog posts out there that show you how to do it with Arduino, and there's a C++ and a Python-based library that show you how to do it. So what I've done is, actually, when you look at the codes to do this, to implement this, it looks remarkably similar to the analog one. That's mainly because I'm hopeful that if I get this working properly, then I can submit it back to the Meadow team, and then this might become a supported sensor. So it looks and it kind of follows their pattern. What you see is rather than supplying an analog port, we actually supply an SPI bus. We have to create one because we have to communicate with the device. It's not just a case of reading things back. We ultimately end up having to write things out to it and then read things back. We have to kind of toggle the modes. And if we then start to look at this, I'm not going to go too deep into this because there's a fair bit to it. Oh, actually, what we can do is just click on that. What you'll end up seeing is, so we create a bus, or we ask the cooler to create a bus, and then we use that bus to be able to convert it, which ultimately, this is, like I say, it's some code that I've converted across from C++. I tried to stay there as short, spend as little time as possible in the C++ code. But it's relatively straightforward to convert across. You'll see we basically set some registers, so there's certain addresses which you can write to, and then there's certain addresses that you can read from. So it's just a bit of byte management. And then it does some conversion, so from, there's a bit of complex maths further down, which there's some mathematical science around it. There's a number of different algorithms that you can follow. This one, much further down, which is here, where you probably aren't too fussed by the inner workings. Here you'll see, so there's a technical documentation on it as to how you can do this. If you click the link from the source, you'll see that there's a bit of a white paper and explaining that this is the most efficient way to do it. Might not always be the most accurate, but then there are other ways that you can do it, which you'll give up performance, but you'll gain accuracy. Apologies for jumping between slides and VS Code. I tried to get the code formatted nicely in this. I either couldn't fit it in the slides or lost the context of the colouring, so I've opted for this approach. Right, heating and cooler element. So I didn't mention that the device here has a 3.3 volt output and a 5 volt output. Now, this device has the cooling element is 12 volts and the heater element is 12 volts, which means we can't power it off the board. And certainly the fridge that I'm in the process of hacking at home is 230 volts. So to keep that simple, I've bought a 230 volt heater as well, so that can remain on the same circuit. But what it does mean is that we have to have two separate circuits now. We have power coming to the heater element and the cooling unit, which is indicated by this. And in order to do that, we can use something that's called a relay. So it's a bit like a switch that you can control with a circuit. So what we do is we put the 12 volts in. My graphics package didn't go above 9-volt battery, so that's what it's showing there. But essentially what you can end up doing is you connect your board, one output to the board, to the relay, and you say, we'll turn on, and then that will turn your unit on. And again, if we just have a quick look at the code, I'm switching the wrong screen. Look at the heater element. The Meadow libraries provide us with relay support. We just tell it the port that we're going to be using to turn it on and off with, and then we just change the state based on whether we're at our target temperature or not. And so closed will actually mean on, open will be off, although some devices invert the way that they treat that. So some might be open by default, some might be closed by default. So sometimes you have to just be aware of that. Okay. I can show you the cooler element code, but it's pretty much identical, short of the comparison here and the pin that you're using. So that makes it relatively straightforward, which is great. So we can ship it, right? We've got temperature control. We can monitor them and react based on that. If you remember, as I mentioned with the heater blanket approach, that is largely inefficient. And the reason is because what you'll end up doing is you're going to get this oscillation effect. Because when you reach the target temperature, there's still going to be residual heat in there even when you turn the element off, which means you're going to overshoot. And then by the time you drop back down to turn it on again, it's going to continue to drop until the heat's generated enough to make a difference. But there are ways to make this more efficient, and this involves some rather complicated, horrible maths that I'm not going to dig into too far, don't worry. So there's something called PID. Is anyone familiar with PID? More than I expected, that's great. When I first hear PID, I always think of personal data, which is always a worrying topic. But if there's not that many people, I assume then if I ask the question how many people use it, that's probably going to be a much lower number. But if I change that, how many people here drive a car? So you all use it. I'll explain why. So PID is a fundamental algorithm in machine control. They use it in the cruise control features in cars. That's how you reach your speed and then you maintain it. But even if you don't have a cruise control feature in your car or don't use it, you will ultimately still be applying that algorithm just in your human brain rather than the car's brain. Because if you imagine you're coming onto a slip road, you're doing 20 miles an hour, you have to reach 70. As you gradually reach your limit, you're not going to keep your foot down until you reach 70 and then lift it off. You're going to actually adjust that with the amount that your foot is on the pedal. And the same is actually true of cooling and braking. So obviously if you're braking, one piece of advice that I never realized until later on in life is that it's much better to lift off almost entirely by the time you actually reach stopping speed, because then you don't get the force that's going to force you back. Sorry, not to make this into advice about driving. So the other point is with PID, I mean, it's, like I said, it's a fundamental algorithm used in machine control, and it's used in nearly every heating control system in the world, so ideal for the topic of this talk. To jump back to the driving analogy, we've got a couple of key variables. So we've got the target, which is our speed limit, 70 miles an hour, or sometimes also called the set point. We've then also got the actual signal, which is sometimes called a process variable, process value, and that's the current speed that we're going at. And ultimately what we say, we pass these into the algorithm. We say we want to be going at 70, we're going at 20. What should we be doing? You should keep your foot flat on the floor at 100%. And then as we start to slowly get closer, say these are made up numbers, 55, 60 miles an hour, and then say maybe lift it up to 80%, and then slowly lift it up more until you're at the point where you're maintaining that speed. You will typically overshoot and undershoot a little bit, because there always needs to be a little bit of correction in there, but you'll end up with a graph a bit like this, which then means it becomes a lot more efficient, because you're not having to heat or put your foot down on the pedal and use fuel up to reach that limit again. You're just gradually adjusting. And then it would there'll always be bumps in the road. Maybe it's someone opening the door to check whether the brew's ready. So you'll get a small drop, but then you'll be able to correct that through the use of this. Right, so now we can actually have a look at this, because we've talked about some rather complicated maths. We can then go and actually look to see how we can use this. And again, singing their tune right now, but so actually the algorithm that I put on the screen was for something called the ideal PID, but there's also something called the standard PID algorithm, and that's what this one is. Quite sometimes a little bit easier to tune, and a fair bit more documentation around making it easier to understand. Essentially what we do, so what you'll see is they ship with a PID controller class, so we can just new it up, give it our three values, P, I, and D. These are magic numbers, and they will change based on any machine that you build. They all come with different thermal properties, so you'll have to consider that when you're tuning. I can't give you any magic answers on what the right values are to use, but quite often, I mean, there is a Windows app on the Microsoft Store. There are many spreadsheets out there online where you can pump your values into it, and it will then graph it for you, and then you can start to tweak them, rather than having to do it live on a machine, which is not always the most fun. And there, on line 21, you'll see it does that line there will actually output that information for you. So then you can put it into one of these tools or into a spreadsheet, and then you can start to actually view how the curve works. So I mentioned we need to give it some bounds to know how much of an output of a result to give us. So we're going between 0 and 1, which is 0% and 100%. And then what you'll end up seeing is we've got our actual and our target. So we're saying what the current temperature is and where we want to get to. And then we just tell it to go and do the calculation. And you can see if you then click into this is their code base, but this is then implementing the algorithm that I mentioned. So you don't have to worry about that. Okay. So PID. That's great. So we now know what power percentage that we can provide to our heater element. The only challenge now is we've only got an on-off switch. So we can't necessarily control that power unless we consider redesigning the circuit. And I don't feel particularly comfortable putting 230 volts in and then somehow safely partitioning it to not burn my board. I've already destroyed a few components. Even last night, I blew up a temperature sensor because I wired it in the wrong way around. That wasn't beer. Well, no, it was beer influenced. Serves me right for having a quick one before practice. But so, as I mentioned, we can't control the power; it's on or off. But we can use another algorithm concept called pulse width modulation, or PWM. And this, again, it's another fairly common used piece of technology. If you're, not sure these are LED lights, you're in a room with LED lighting, that's how they can stay bright, but actually they're not on all the time. They're just on enough that the human eye doesn't see them flickering. And actually that's why if you take a photo and you see the horizontal black lines, I think they're typically horizontal, that's because you've got interference between the speed of the lights and the speed of your camera shutter. And there's only kind of two key components to this. You've got how long your period is, which is dictated by hertz. So 1 hertz is 1 second, 2 hertz is half a second. So go in the opposite direction to what you think in terms of length. And then you've got what's called the duty cycle. So if you've got 1 hertz and a duty cycle of 50%, it's on for half a second, off for half a second. And then this means that we can go and look at how to use this in code. And yet again, we've got some relatively short amounts of code. So they come, many devices actually come with hardware PWM support. I've opted not for that, just so I could transfer this across, in theory, between different boards or technologies without having to worry about whether that specific D2 port I've chosen does support it on all of them. And again, the Meadow libraries do provide you with a soft PWM support. And you can see here that what we'll end up doing is we will tell it a duty cycle of 1, so it's on for 100% initially, and then a frequency of 0.1 hertz, so it's 10 seconds. Because the other thing with relays, they have a limited lifespan. These here are mechanical, because they make for a slightly better demo. And I had some kicking around in the hack kit. But I typically recommend that you use a solid state relay. They are a bit chunkier. They do heat up, but you can cool those with heat sinks. But they have a much longer lifespan because they don't have any moving parts. They don't make any sound, but I'm not really sure that the sound it's too worrying. Unless you're sitting in the speaker lounge, warming up and disturbing other people. Yes, and then so what this code is doing, like I say, we've got the D2, we're pointing at the port that we want to turn on and off. And then we're using the PID controller again, we're calculating that percentage that we want to apply, and then we're applying that to the duty cycle. So what it'll then mean is we've got a 10-second period, so if we've got 50%, it'll be on for 5 seconds, off for 5 seconds. And you could play around with your durations as you see fit, based on the mechanics that you've got. Because again, so with this heater element that I've got, it takes a little bit of time sometimes to heat up. So if you're constantly turning it on and off, you're not always going to get a high output. And the thing that really scared me as I was writing the code is in their XML documentation, it does say this class is not yet implemented. I can safely say it is, because it works. But I will need to feed that back to them at some point. Right, where are we at? Okay. So, just before we do the demo, the talk is titled If.NET Brewed Beer. So .NET is running on the Meadow board. It's not the only part of the setup that is in the code base. So at the moment there's an Azure-based API. Well, there's an API, ASP.NET web API and websites, and then there's Azure hosts that make it a little bit easier to develop. And you've got the fancy dashboard, which is great because when I keep sending up requests wrong and causing exceptions, it's not killing the app, but I can then go to the dashboard and actually see why. And I've got that running on a Raspberry Pi. We've then got the Meadow board, so that's running .NET Standard 2.1 on here. By going through the mono runtime, and then .NET MAUI application that I'm running on a Mac. So I'm not actually going anywhere near Windows for any of this, which goes to show the power of .NET that we have these days. Yes. So I'm going to try and get this running now. Now, I apologize that the cable was a lot shorter than I had intended, but what I can show you here is, you can have a look at the development environment as well. So you could just plug your board straight into the device, and in the run and debug section within VS Code, you can then choose your device. And this will then run it up, and you can hit breakpoints in there as well. Wrong window. full screen, isn't it? That's why it won't let me. Oh, it's horrible now that it's zoomed in. I can't see anything. There's a problem. No, that's okay. Oh, no, we have it. It is running. Let me click on it over here. So what you'll see is we have a screen. Have a screen. So I will be honest, to make it a more animated demo, I've actually simulated the temperature sensor. So that's another thing that comes with the Meadow library. You can replace your sensors with simulated sensors, and you can't give it particularly complex thermal models. It'll do like a sine wave or a sawtooth between values, or just random values. If you wanted a more complex one, then you have to implement it yourself, but you can certainly do that. And you'll see here that the fan's kicking in. That's because we're cooling at 36%. I don't know if you can hear that. It is still running, but it's not actually going. It's just because it's been forced. And then we'll see, once it then starts to drop down, you'll see it'll then correct itself to start heating. Clicking away now. I'll be honest, I was a little worried bringing this in through security, but they didn't seem too phased by it. As soon as I said I was for the tech conference, he didn't seem to worry. Right, that's... and then I'd just like to give you a little brief overview, because I've mentioned all of the kind of the bits that we've done, but just to give you a bigger picture of how this all pieces together. So when you create a Meadow application, what you'll end up getting is a Meadow app, and that might look... no, it won't look similar to a typical .NET app. So you create an app, you inherit from app, and you tell it what type of board you're connecting to. So I say this is a V2. I've also got a V1. You have to change that in code. Interestingly, you can also replace it with Raspberry Pi. So you could, in theory, run this on a Pi with Meadow Linux. I haven't tried it. I can't say exactly how well it works, but it does get me quite excited. So if you can, in theory, have the same code that could run on all of the devices, then that becomes really quite fancy. Another possible option, if you want to use a Pi, is there was a talk earlier with Pete Gallagher, so yesterday, being able to install .NET on a Pi, and you can run that. But obviously, I mean, a Pi is a much more powerful device than this, although you can probably buy one sometimes cheaper. So you've got the ability to create your app, and then you typically have these controllers that we create. There is the ability, I showed you, there is the display, and that's almost just like doing a console.write line. It's only got 4 lines on this display and up to 20 characters wide. Again, everything you point it at, the pins you want to use to control it. I mentioned the Wi-Fi, so you can configure it to connect, and these always get thrown away during the deployment process, so it's not possible to read these once it's on the device. And then the other nice thing is that because it's .NET, we can then start to look at potentially sharing code. So if we've got this sending data up to an API, we've got a mobile client sending data up to an API, you could have one project that defines that model. Obviously, sometimes you might want to design this to be have a much smaller packet size, because you don't want to be wasting bandwidth. Certainly if it's out somewhere remotely, you might need to be using 3G or even potentially worse, or lesser technology. So you always need to be considering that. So you don't want to be making it to the point where you're going to lose connectivity. And you can configure it like many applications. For some reason, they've chosen YAML, because we all love a YAML, right? But you can like any app config. These are my own that I've added in, and you can then read it in just like, where do we do that? Oh, settings, it's a property that's already populated for you. You don't even have to read it. It's already populated for you. Okay, that's actually gone a little bit quicker than I had originally demoed. So what I would like to say is this is running. Oop, that's all right. It's been running for a little bit of time, so I've got a little bit. If I'd have left it longer, it would have been obviously much bigger. But cheers to everyone, and thank you for coming. The code base is there on the first link, and there's a getting started guide for the Meadow thing. I'm more than happy to answer any questions if anyone has, or you want them welcome to come and poke the fan like I just did. I might power that bit off.
Thought about removing the relay and just having it modulating the voltage going to the heater, so you can then, rather than having it going on and off with population and duty cycles, etc., you just control the voltage.
This is what I should have asked you.
So, it just means your PID will be a little bit cleaner, because you're then just setting the voltage to, like, say, 8 volts, which will then give a certain amount of heating.
Okay.
So 12 volts where it's fully heating.
Yeah.
You can control it a little bit easier. You might not burn out a mechanical relay then, which is switching on.
Yeah. What about transitioning to something like a AC supply then?
You do, so it'll be a power MOSFET or something like that.
Yeah, okay.
It'll still run through. So what you're doing is controlling the voltage. So instead of it being 230 volts, it might only be 150 volts.
Yes, okay.
And you're kind of going through that. So it's another way of looking at it. Not
That's a V2 then, isn't it? Yeah.
more beer required.
Yeah.
Are you planning to put this all in?
Yeah. Sorry.
Has your beer game improved with creating this?
It's left me distracted, that's for sure. I had as a jokey gift, my wife bought me a brewing thing for Christmas. I had intended to try and actually get that done and bring it with me, but I piled my effort into the IoT rather than the drinking. So it's healthier for you, that's for sure. Ooh, no, okay. Any other questions? Yep.
Considering it's like an IoT device, was using MQTT ever come into the mix?
Pretty sure you can. You can, yeah.
Would the board be able to support it? 'Cause I know it's not.
Yeah, you can, yeah. You can open up a socket as well and pump, yeah. I think there is a library that they provide for support for that. Would anyone? So I need a good name for it. So if anyone wants to come up with a good name, I'm more than happy to donate a beer. It might be quite warm now, though. The heater out. No, it's okay. No pressure. Fred.
He used too many of those, didn't he?
Too many friends. Sorry.
What's the next step then? You've got your demo with your article box. What's next?
So I am, like I said, I want to get the bit going up to Aspire so I can get the telemetry up. Like I say, I blew up a temperature sensor, so I need to go and replace that when I get home. And then, I mean, I was hoping that this would be a working prototype. I'm not convinced I've got enough power in that, so I'm going to have to actually test it when I get back. There's only a single 12 volt. It's only like 15 centimetres by 5 centimetres. It's a tiny little element. It puts out a fair bit of power, like I say, it can get up to 70, 80 degrees. But it's just actually working out whether that's suitable to kind of get up quickly. And I'm still trying to get permission to properly dismantle the fridge in the garage.
You need one of those TISM fridges, so you can put your Maui out on.
There you go, yes, yeah. And that can then hook into it, yeah? Yeah. Crowdfund my own brewing operation. Yes, but like I say, so I'm working with a buddy of mine. He's using BrewPi. We're going to try and persuade him to put this on and compare the two. And obviously brew some beer and get drunk.
Side effect of the project.
Indeed. Excellent. Okay.
Cool. Thank you.
Thank you.